Alright, so let's continue from where we had left off in the previous video. If you remember, the last point that we had discussed was about the units of force, the other units. In other units, we had the gravitational unit and we had kgf and gf, kilogram force and the gram force. But this is not what we have to worry ourselves with too much about. These are the ones that we have to remember. SI unit, newtons, and CGS unit, dyne. And please remember, 1 newton is equal to 10 to the power 5 dyne. Now we have come to the most important part of the chapter, and that is the turning effect of the force. As we had already discussed, if you apply a force, there can be the turning or the rotational effect also. So that turning effect of force we have to study quantitatively over here in terms of a formula and in terms of understanding how it works. So first of all, you have to remember that there are three terms. Moment of force. Please remember, it is not a movement, as most of the children make mistakes most of the time. We have moment of force, M-O-M-E-N-T, moment of force. Oblique means there is another name also for it, turning effect of force, as well as torque. Okay, so please remember these words, torque, which also means turning effect of force, and or moment of force. So these three terms, any one of these three terms could be used. Now, what exactly is that turning effect of force? If you remember from the previous video, I had taken up this example. Now if you see, this is a pulley that is hinged or pivoted at this point with the help of this metallic rod, which is attached to this solid support. Now, if you apply a force at this particular end, as I have shown in the direction like this, what effect will it produce? It will turn the pulley like this. It will try to rotate the pulley like this. Now, are you able to see the direction in which my hand is moving? Now, whenever a thing rotates, there are two directions of rotation. One is clockwise, which is exactly the case that I am referring to, clockwise. Okay, so if you apply the force over here, this particular pulley will move clockwise like this. Okay, so because of this force, the turning effect that has been produced in this pulley is in a direction which is clockwise. Okay, so the direction, as you can see, I have mentioned clockwise turn. Okay, why is this clockwise turn taking place? It is because of this force F that it is taking place. Now, coming to another diagram over here, the difference between this and this diagram is very minute. That is, instead of applying the force on the left hand corner of the pulley, this time I have applied the force on the right hand side of the pulley, and the forces in both cases are being applied upwards. So now obviously, logically, if you visualize, this force will also create a turning effect, but this turning effect will be in a direction which is opposite to the direction that was prevalent here. Here you had a direction like this, which was clockwise. Here you will have an opposite direction, which is the anti-clockwise direction or the anti-clockwise turning effect. Okay, so the turning effect or the moment of force or the torque, it has a direction also, which brings us to the fact that torque or the moment of force, it's a vector quantity. It has a magnitude as well as a direction. So direction will either be clockwise or it will be anti-clockwise. Now, coming to the magnitude part of it, torque has a formula. Torque is equal to force. So where is that force over here? Over here, if we consider this particular example, this is the force. So this force obviously will have its value. In case of numericals, you will be given this F value multiplied by, please read this part carefully, perpendicular distance of the line of action of force from the pivot. So now let's have a look over here in this particular figure. Where is the line of action of force? So if the force is acting like this, I can draw the line of action of force like this. So this is the line of action of force, and perpendicular direction of the line of action of force from the pivot. So where is the pivot in this case? The pivot here is labeled as P. So it is this distance D that I am talking about. Okay. So this distance D between the line of action of force and the pivot, and in case the pivot is in place of pivot, you can also use the word the axis of rotation. So the axis of rotation is going through this point. So you can imagine two parallel lines to be running, and that perpendicular distance between them is to be treated as D. So the torque formula is F multiplied by this perpendicular distance. Please remember, it is always the perpendicular distance from the line of application of force or the action of force to the pivot. So this formula can simply be written as torque is equal to force multiplied by distance. Please remember, this distance is the perpendicular distance. Alright, and torque is a vector quantity, so it will have a formula, it will have a value. The value answer will come once you put the individual values, and there will be a direction also. So that's a vector quantity. Now, this concept of the turning effect of force is better described over here in this example. This is an example of a seesaw. Every child has seen this once in his lifetime. So you can see there is a pivot or the fixed or the hinged point in between. Then there's this wooden or metallic plate that they have. One on either sides we have two children sitting, one child over here, one child over here. Now obviously, if a child sits over here, what is he going to do? He is going to exert some force over here downwards in this direction. Why? Because this force is nothing but the weight of the boy. Okay, so this is acting downwards. Now this is the pivot. As of now, I am not going to take this into consideration. I am having this boy sitting on this at this end. He is trying to force the right hand end down. Okay, so you can see the direction. This effect of this particular force, what is it going to do? It is going to apparently bring this right end of this seesaw down in this fashion. Okay, so as you can see, this is in a clockwise direction. So this is producing a clockwise turning effect or the clockwise moment, or you can also say clockwise torque. Okay, so similarly, the boy sitting on the left hand side also has his own individual weight. So let his weight be F dash. So that weight is creating the force downwards. What is his distance, perpendicular distance from the pivot? His distance is D dash. Similarly, the distance of this boy from the pivot was D. Okay, so supposing this is the situation. Now, how many turning effects are being created? Now you see, because of this boy, the clockwise turning effect is there. So clockwise torque is equal to, now what am I going to use? I am going to use the torque formula that I had discussed just now, force multiplied by the distance. So which torque am I talking about? I am talking about the clockwise torque just now. So this is the clockwise torque. So for this I will take this force and this distance. Okay, so F into D. Whatever the magnitude, this is known as the magnitude of this clockwise moment or magnitude of the clockwise torque. Similarly, if we have a look at this particular boy, he is producing an anti-clockwise turn. So anti-clockwise torque, the value or the formula, if we put, it will be this force multiplied by this distance about the pivot. Okay, so F dash into D dash. So right now in this particular system, there are two turning effects because of two different forces that are taking place. One is producing the clockwise torque, the other one is producing the anti-clockwise torque. So now the obvious question I have written over here for you just to save time. Think and decide if these two moments due to F and F dash about the pivot P are assisting and helping each other or they are opposing each other. So how do we know whether they are actually helping each other or opposing? So you see, you will have to look at the direction. This torque is trying to produce a clockwise turning effect. whereas this is going to produce an anti-clockwise turning effect. So they are basically trying to cancel each other out, or they are opposing each other. Okay, so that is what we understand with the term, by the term torque. Now, what are the factors influencing the torque or the moment of force? So there are two factors. So these two factors obviously you can get from the formula itself. Torque depends upon F and D. Okay, so magnitude of the force acting. If F value is more, the torque will be more. The turning effect will be more. The person will try to bring this end or this end down with a more torque. Okay. The second factor that influences is perpendicular distance of the line of action of force from the pivot. So obviously from the formula you can have a look. This D is the perpendicular distance of the line of action of force from the pivot. So this distance. Similarly, line of action of force and the pivot, this distance. Okay. So these are the two factors. You increase these two values, the overall torque increases. You reduce these two values, the overall torque decreases. Now, this was the theoretical part, the formula and the other things. Now let us first talk about the practical aspects. Where do we actually see this torque or the turning effect in our real life? So for your assistance, I have drawn one small diagram over here. This is the diagram of a door frame. This, as you can see, it's a door frame and this is the door. Now these are the two hinges that let me just mention this as these two are the hinges. Okay, so the fixed supports, you can also call them as the pivot points, P, the fixed points. So now this is the handle. I have mentioned door handle. Now if you want to open this door, what are you going to do? You are going to hold the handle and you are going to apply the force outwards so that it opens outwards. Okay, now effectively once you apply the force at the handle, you are providing an F to the handle. Okay, now what is the effect of this force? The effect of this force is to produce a turn of the door. Okay, either outwards or inwards. So in this case, if somebody wants to know what is the torque or what is the moment of this force, how are you going to calculate it? So once again we will have torque in terms of force. Which force is this? The force that you are applying at the door handle, multiplied by the distance. Now what is this distance going to be? Please remember, perpendicular distance of the line of action of force. So this is the line of action of force, because here we are applying the force and these are the pivots. So this distance D is what we are talking about over here. So this distance D, once you put it over here, the overall value you will be able to get. So this force is creating a turning effect over here. You can either open the door or close the door. Now, if you have really understood this entire thing, there's a question for you all. Why is it that the door handle is always to the farther end of the door? What will happen if we put the handle, in place of putting it over here, if we put the handle over here? If we put the handle, let's say, in the middle of the door, what will happen? Obviously, if you visualize such a scenario, what you will have to do is, if you hold the door over here with your hands, door handle over here with your hands, you will have to apply much more force to open the door. Why is that so? Because if you apply the force over here, the perpendicular distance from the pivot has been reduced to this much. Earlier that perpendicular distance was more, so the torque was more. But then, since in this particular case the perpendicular distance has reduced drastically, so this distance has dropped. Therefore, the force that you have to apply at the door handle, you will have to increase that force to maintain the torque required to open the door. I hope you are understanding this particular scenario. You see, the closer you go to the hinge, the closer you go to the pivot to apply the force, D is dropping. So in order to maintain the same torque, you will have to increase the force. That is the reason why we always keep the door handle farthest from the pivot, which is obviously this point. Okay, so I hope you have understood this particular aspect. Now, torque obviously is a physical quantity, it has a magnitude, it is a vector quantity, so it has a direction also. Now coming to the units, once again, the SI and the CGS units. SI unit is Newton meter and CGS unit is dyne centimeter. Now for those who are wondering how did this Newton meter come, so it is very simple. It comes from the formula torque, as we have already discussed a couple of times now. Torque is force multiplied by the distance. The SI unit of force is newtons and the SI unit of distance is meter. So that is how we get the SI unit of torque, Newton meter. Similarly, the CGS unit of force was dyne and CGS unit for distance was centimeter. Therefore, dyne centimeter is the CGS unit for torque. Please remember these two units. Now once again, before we finish up with the session, the relationship between this is a question that has been asked a couple of times. Relationship between SI and CGS units of torque. Now SI unit of torque is Newton meter, CGS unit is dyne centimeter. So what is the relationship? Now the relationship is 1 Newton is equal to 10 to the power 5 dyne. 1 Newton is equal to 10 to the power 5 dyne. Now how does this come about? Once again we'll start from here. You see, 1 Newton is equal to 10 to the power 5 dyne. We had already discussed in the previous lecture when we were studying force. 1 Newton is equal to 10 to the power 5 dyne. So I have converted Newton, I have converted the Newton part into dyne. Now what remains is meter into centimeter. So in the next line you will see 1 meter is equal to 10 to the power 2 centimeter. Okay, so Newton part I have converted to dyne, meter part I have converted to centimeter. So now when I combine these two together, 1 Newton meter will be equal to 10 to the power 5 multiplied by 10 to the power 2 dyne centimeter. 10 to the power 5 into 10 to the power 2 will make it 10 to the power 7 dyne centimeters. So effectively I can write down 1 Newton meter is equal to 10 to the power 7 dyne centimeter. This is the relationship that they had asked. So before moving ahead, let us just have a look for half a minute, and I hope that you all have understood this. Okay, so now having studied most of the theory and the formula involved in the torque, let us solve a simple questions, simple numerical on the same concept. Please read the question carefully. A body is pivoted at a point. A force of 10 newtons is applied at a distance of 30 centimeter from the pivot. Okay, so what is the scenario? There is a body. Now let's make a rough diagram in case that actually helps us to solve the question. Suppose this is a body, okay, and it is pivoted over here at point P, and there is a force acting like this, F. What is the value of this force? The value of this force is 10 newtons. Okay, at a distance of 30 centimeter from the pivot. Where is the pivot? This is the pivot. Where is the force? This is the force. So this distance D is what they are talking about. Okay, so as you can see, this distance D is given as 30 centimeters. So the first thing that you do is you convert this into SI system, so that will become 0.30 meters. So obviously since this is centimeter, you divide it by 100, you bring that information into SI unit, which is 0.3 meters. So what are they asking now? Calculate the moment of force. So moment of force basically means torque. The formula for torque is force multiplied by the perpendicular distance. So force is 10 Newton, which is already in SI unit, so we don't need to change anything here, multiplied by the distance. So that distance is 0.30 meters. So once you multiply, this will become 3.0 or simply 3 Newton meters. Okay, so the torque or the turning effect produced by this force is 3 Newton meter. Now obviously I have already mentioned that torque needs a direction also. Now this was a hypothetical diagram that I had drawn to make our calculation and understanding easy. The question had not specified the direction of the force. It could have been up also, it could have been down also. Okay, so in this particular case we will say that this is, what kind of a direction is this? This is clockwise direction. So we can write clockwise. Okay, so this is the magnitude, this is the unit, and this is the direction of the torque or the moment of force. So this is a very simple example on how to calculate the moment of force or the torque. So now children, having understood this part, now we have moved to the next problem. Now this is not exactly a question, this is for the explanation of multiple forces acting. Now you see, this is a uniform meter rule. Please have a look at the diagram that I have drawn. This is a uniform meter rule. Now there is a meaning attached to each and every word over here. Uniform means that the rule that extends from here to here, it has uniform mass. Okay, so it is equally thick throughout. Okay, the concentration of the mass present throughout this ruler is uniform. Okay, and obviously meter means it's a 1 meter rule or a 100 centimeter rule. Okay, so that makes it a uniform meter rule. Now it is pivoted, as you can see, at point P once again. So this is the fixed point, this will not move. Okay, these are the free two ends. Okay, now there are two forces acting. One is F1 of 10 newtons, the other one is F2 of 20 newtons. The values are different, but the distances of these two forces from the pivot, they are same. So 0.5 meter here also, 0.5 meter here also. So now what are we going to study using this example? Please read this. Finding out the net moment or the resultant moment about a pivot. So in this case the pivot is P when more than one force is present. Okay, so had we just overlooked this force, had this been the only force, this would have produced a clockwise moment. But then there are two forces acting here, so they will produce two turning effects. Let us see whether they are in the same direction or in different directions. So this produces a clockwise turn and this produces an anti-clockwise turn. So are they opposite? Yes, they are opposite. One is trying to turn it like this, the other one is trying to turn it like this. Now for sign convention, anti-clockwise torque or turn will always be taken with a positive sign and clockwise will always be taken with a negative sign. So how do we find out the net moment or the resultant moment because of these two forces? So first you calculate anti-clockwise moment about